Okay, we are going to learn section 6.8 here, natural logarithms. And the book takes and just kind of drops this number, this irrational number e on you out of nowhere, out of thin air. And I don't like how they do that. I'm going to give you a little explanation for what the number e is and why it's useful and why it shows up in this section, okay? So let's start by talking about the compound interest formula, which is this right here. It's principal times 1 plus the rate divided by the number of times you compound, raised to the n, which is the number of times you compound, times t, which is in years, okay? And so this formula here, we're going to play around with this formula, and we're going to start with a very, very simple example. We are going to start with a situation where you have, we're investing $1 for 1 year at 100% interest, and we're going to start by compounding just one time per year. So what that means is that you put the dollar in the account, you'll wait a year, and then after 1 year, we will compound. That is, we'll give you the interest on your dollar. If it's 100% interest, you'll earn 100% of your dollar, so you'll get a dollar more. So you'll have $2 at the end of the year. So what that means. So that's great, right? You've doubled your money. Fantastic. Then what we're going to look at is what happens if we compound twice per year. So let's think about what that would be. That means that 6 months through the year, we would compound the interest. Or that means that we would give you the interest on that 6 months. So that means that if you invested a dollar at 100%, sometime in June, halfway through the year, you would get 50 cents, which is 100% interest, but only half the year. So 100% would be the whole dollar if you went the whole year, but you're only going half the year. So you get 50 cents, and that would get wrapped into your principal. So now, starting in June, you've got $1.50 in your account, and that's going to accrue interest for the next 6 months. And then we compound again. Again, 100% interest, half the year would be half of $1.50 is 75 cents. So you'd get another 75 cents on top of your $1.50. So you'd have $2.25. Pretty good deal, right? Now you've made 25 cents more than what you would have if you just compounded once. So then maybe you get to thinking like, what if I compound more, right? So well, let's check our math first. So if I compound twice, I get $2.25. And then so if I compound more, watch what happens. I start to make more money. There's $2.37. $2.44, and this is, if I compounded 10 times per year, I'm at $2.59. But what you notice is that there's not a big jump from 9 to 10, right? You're only making an extra penny there. Pretty big jump from 0 or from 1 to 2, not so much from 9 to 10. And so it turns out that there's some limit on the number of times that you can compound to where it's beneficial. Okay, so let's crank n up even more here. Let's go 100 times. Okay, so 100 times we're at 270. 1,000 times per year we're at 271, around 272, I guess. And then we can just keep going. And what you end up with is you're getting very close to this 2.71828, and it will keep, it'll get smaller and smaller and as we go until we can kind of overload the calculator. This number that it approaches is a number called E. Whoops. Here's the number E. Okay, so it has a name. It's an irrational number, and that's where it comes from. Okay, it shows up all the time in continuous growth, where you're compounding an infinite number of times per year. And that just means that you're compounding all the time. And so this is a good example of this is like if you invest money in the stock market, your money is constantly, the value of your the stocks that you've purchased is constantly changing depending on the market, and all that money is getting all that value is getting wrapped up together and is going to be constantly compounded. So if you make 1% today on your stocks go up 1%, that 1% you get to keep that 1%. It's not like you have to wait the whole year before it compounds. All right, so that's where the number E comes from. Very useful in continuous growth. And this is, you can even think of it like a bacteria in a petri dish. I mean, just things where the growth is nearly continuous, all right? You get this type of function here. This is the continuous compound interest formula. So if you compound infinite number of times per year, this is the formula that you end up with. We're going to come back to that in a second. Okay, So let's bring up this thing here. We'll see if we overload the computer at all here. Okay, so we are going to look at 6.8. We'll do some actual examples here. You can see what this is. They give a bunch of explanation here, a lot of which I explained. You can see here is e to the x, so the exponential function with a base e. And then its inverse is the logarithm with a base e of x, or with a base e. And we denote that because it comes up so frequently in the sciences, and it's a natural extension of continuous growth, we call it the natural logarithm, and we denote it ln. So here we have like ln of 4 equals x. That is the same as the log base e of 4 equals x. Okay, because log base e gets shortened to just ln, right? So in this example here, right, the following is a logarithm. If I have e to the x equals 8, I can rewrite that as log base e of 8 equals x, but you'll never see it written like this because log base e is ln of 8, okay? So let's look at the next one here. We want to write natural log of 10 equals x. We want to write that in exponential form. Well, this is just log base e of 10 equals x. And so this changes to 10 equals e to the x. All right, so you just have to remember that when you see ln, it's going to be log base e. If it helps to write it out explicitly like that, then certainly feel free to do that. Okay, so we can do all the same properties with logarithms that we could before. So we can take the natural log 10 minus natural log of 8, and we can simplify it. In other words, we can condense it down. So the first thing I always look for is numbers that can be put into the exponent inside of the logarithm, and this is there's a 3 here that can be moved up. So this becomes the natural log of 10 to the 3rd power minus the natural log of 8. Now I'm subtracting logarithms, and that can be condensed down using division. So this would be natural log of 10 cubed over 8. 10 cubed is 1,000, so this ends up being natural log of 1,000 over 8. You can simplify that if you want. I'm not worried about it. So there's your simplified version of that expression. Okay. Next, solve the following equation. Again, all the same methods that we've learned already apply to natural logarithms. So we're going to add 5 to both sides. So I get 4e to the negative 2x equals 8. Divide by 4. I get e to the negative 2x equals 2. And now at this point, what I'm going to do is I'm going to take the log base e of both sides. In other words, I'm going to take the natural log of both sides, natural log at the left and of the right. These undo each other. They're inverses of each other. So I get negative 2x equals natural log of 2. All right? And then I'm going to divide both sides by negative 2. Now, something I haven't said yet that is really important is that the natural log has a button in the calculator. It's right here. So we can type natural log, and then we can put natural log of, what do we have, 2 divided by negative 2. And it'll compute it as negative 0.347. I have this in Desmos as well. Bring that up real quick. So you can probably the easiest thing is just to type ln. Okay, it'll automatically go to natural log, but if you look at the calculator keyboard here, you just go to functions, and I think it's under miscellaneous. Yes, there's ln right there. Okay, so different ways that you can do it in Desmos. Let's bring back this. All right, solve the following equation. Let's solve a logarithmic equation now. So this one we will take and first divide by 3. Well, we've actually got 2 options. I think the easiest thing is to divide by 3 first. So I get natural log of 4x equals 8. And then to undo a natural log, which is log base e, I'm going to take the e, I'm going to exponentiate both sides of the base e. So e to the left, those are inverses, and e to the right, which would be e to the 8. Okay, and one thing I should say right here is you can change this using the definition of a logarithm. I just think thinking about it algebraically is more useful. So then I'll divide both sides by 4. And then you can put that into your calculator as well. Your graphing calculator has an E button, and then it's let's see, second, and then right here the division symbol. And then your Desmos, you just type the letter E, okay? And so you end up with, whatever it is, it's e to the 8 over 4. It's some ugly decimal, I assume. I'm not too worried about it. Okay, last thing here, continuously compounded interest. If interest is continuously compounded, then the amount in an account after 2 years is given by this formula. So P is the principal, R is the interest rate as a decimal, and T is time in years, okay? So let's solve a problem here. When Angelina was born, her grandparents deposited $3,000 into a college savings account paying 4% interest continuously compounded. Assuming there's no deposits or withdrawals from the account, what will the balance be after 10 years? So we need to set this up using what we sometimes call the PERT formula, P-E-R-T there. So the PERT formula, the continuously compounded interest formula, looks like this. A equals P, which is the principal, so 3,000, times E, which is just a number, remember, raised to the RT. The interest rate is 4%, so 0.04, times the amount of time. We want to know, so times 10. All right, and so we can just put that into the calculator, or you can type it into Desmos. I've got the calculator right here, so I'm just going to go 3,000 times E raised to the 0.04 times 10. And Desmos, you just type in the same expression. So you end up with 44, 75, 47. So all right. Okay. How long will it take to the balance to reach at least $10,000? So what we're going to do then is we need to take this expression, and what we're trying to figure out is time, right? We want to know after how long. We're just going to leave T in there. Now you can do this, so 10,000, and this is actually probably, oops, that was 30,000. So 3,000 times e to the 0.04 t. So you can solve this equation if you want. That's one way to do it. Probably the easiest way is just to use your graphing calculator, and that's probably the most realistic way. So what you're going to do is just go to your graphing calculator. Let's go with a new Desmos screen here. Let's see how long it takes to load. A while, it turns out. Okay, and then we're going to take and graph 3,000 times e raised to the 0.04x, and we want to know when that graph crosses 10,000. Okay, so we need to look higher up on the y-axis here. Let's go up to, I don't know, 15,000 maybe, and we should be able to see it. 15, 2, 3. Now it looks like it's a little bit to the right here, so I will just sort of scoot the graph over to the right, and the intersection here is after 30 years, about 30 or 31 years. It'll be so right there, about 31 years is when it'll finally reach $10,000. Okay, so and you can see that that's more than tripling the money. But I think that pretty much wraps up 6.8, natural logs and exponential, continuously compounded exponential growth. And we're approaching the end of chapter 6.